Welcome to Algebra 2. Today we've got section 6.1, exponential growth and decay functions. Before we begin, I just want you to think about where you might have heard the word exponential before. If something changes exponentially, hopefully you're associating that with growing very, very rapidly, because that's exactly what's this next type of function that we're going to explore, and that's exactly how it behaves. So if it's an exponential growth, it's going to grow really, really rapidly. And if it's going to decay, it's going to it's going to become smaller very, very rapidly. Exponential means it happens in a hurry. All right, so first let's talk about exponential growth functions. In this type of function, you can see here is our basic form right here, y equals a times b to the x. Remember the order of operations. I'd almost like it if it were y equals a times b to the x. You might want to write it like that off to the side. Real tempting to do a times b, but remember that exponent is only applying to the b. But if you look at that function, our input and output, our x and our y, the input is the exponent. So if you think about what an exponent does, it multiplies in over and over and over again. It makes numbers huge in a hurry. So now every time our x goes up by a little bit, that is a power going up by a little bit. That's what causes that really rapid, that exponential growth or decay as well. Okay, so that a variable out in front, that's going to act kind of like our vertical stretch or shrink that we've seen before. And we've seen that on all of our functions in the past, but that still is there. It could possibly vertical flip, I guess, if a was negative. But it is affecting the graph of the function. It's not having that x, that exponent of x act on it. Okay, so if a is greater than 0 and b is greater than 1, that means the thing raised to the power is bigger than 1, then it represents exponential growth. A number bigger than 1, when we raise that to a power, it's going to get bigger. It's growing. Okay, b is called the growth factor, so it actually does have a name. All right, so if we take a look at our parent function, the graph down below, you can see that as our x increases, as we move from left to right, the graph gains height very, very rapidly as that exponent increases. It is a continuous graph, so we could raise something to the 4.371 power, and we'd still get an output. And you can see down below, the domain of an exponential function is all real numbers. We can plug anything into it, and the range, at least for this parent function, is y greater than 0. Again, if we adjusted that function, we'll see this later on, by raising or lowering it, shifting it up or down, that will affect the range as well. But we also see this behavior called an asymptote. Right? An asymptote, it's a line that a graph, it doesn't necessarily have to be a line, leave that for pre-calculus, but it's some graph that that our graph approaches more and more closely. So if we take a look at this, you can see that it levels off in height as we go to the left on the x-axis. It doesn't ever cross it and go below. It just gets drawn closer and closer and closer to that x-axis. A colleague of mine says that asymptotes suck. And what he means by that is that, that they pull the graph closer and closer and closer. So it's kind of a funny way of thinking of it. Let's look at what happens for an exponential decay function. You can see that the function itself, it's still y equals a times b to the x, but in this case, b is something between 0 and 1. So it is something less than 1. If I raise a number that's less than 1 to a power, and I increase that power, it just keeps getting smaller and smaller and smaller. So now our graph kind of looks like a horizontal flip, really. Now you can see it's losing height very rapidly, and it still has that asymptote action. It still gets drawn closer to the x-axis for its parent function. All right, so now we've seen what they look like. The domain is still all real numbers. The range hasn't changed. It's still y values greater than 0. And then lastly, an application for exponential functions. You're going to see a lot of interest problems here. So the type that we're going to be exploring today is called compound interest, where it is not done continuously. Okay, so you can see it's just done some number of times per year. All right, and you can see our formula, it does kind of look like our y equals a times b to the x power, but now you can see that the a value is represented by p, and then the 1 plus r over n, that's making up our b value, and then n times t is making up that exponent. Now, one thing to realize, n times per year means that, let's just make a little table here. We want to look out for keywords when we're doing these types of problems, so it might be a good idea to get this vocabulary out of the way right now. So if it means per year, if I see a word like quarterly, that means 4 times per year. If I see monthly, that would be 12 times per year. If I see annually, that means 1 time per year. Daily, that would be 365 times per year. Weekly, that would be 52 times per year. And those numbers won't be given to us. We have to know, based on the word that we see, what to plug in for the n value. So that can help just having that vocabulary there. All right, so let's look at our first task. We're going to evaluate some different expressions here, and you can see these are exponential functions, and we're just going to get our feet wet by plugging in some values. Firstly, let's do number 6 here. That's 6 times 2 to the negative second. This is part A, where we're plugging in a negative 2 for x. All right, well, that would be 6 times, I got to do the exponent first, order of operations. 2 to the negative first is like 1 over 2 to the second. That's like 6 times 1/4, which is 6/4, which is 3/2. Now, yes, we could use a calculator and we could just type that in and get our answer, but I think it's, especially in the notes here, it's especially useful to see how those exponent rules tie in with these exponential functions. Part B for that problem says, what happens when x equals 3? Well, then it's 6 times 2 to the third. Got to do the exponent first. That's 6 times 8, and it's 48. Now let's look at number 8 for part A there. Here I've got 2 to the negative second and then minus 2. Have to do the exponent first. That's 1 over 2 squared again, and then I'll subtract 2 from that result. That is 1/4 minus 2, which would be 1 3/4. But I like improper fractions. That would be 1/4 minus 8/4. If I get a common denominator, negative 7/4 should be my answer. Now, to the keen-eyed student, you may be thinking, wait, Mr. Hartz, the range was supposed to be all y values that are greater than 0 for these, right? Well, yeah, if it's the parent function, but what we've done to our function here, if you look closely, is we have subtracted 2 from it. So that whole graph is shifted down 2 units. So now, instead of seeing a graph that looks like this, we see a graph that looks like this. So it is possible for these to output negative numbers if they are shifted down. And we'll explore that in a later section. I think it's 6.4 maybe that we look at transformations, but definitely affects the asymptote. Letter B, 2 to the third and then minus 2. Well, 2 to the third is 8, then I subtract 2, that is 6. So practice plugging in numbers as exponents and also how to handle our order of operations once we've plugged them in. That's our first objective. Next, we're going to use our abilities here, plugging in values to make a table of values and graph a function. First, what we were supposed to do, though, is tell whether or not it's growth or decay that function is representing, then graph it. All right, so for number 12, here you'll notice the thing raised to the changing power is a 1/8. In that case, that 1/8 is between 0 and 1, so this is our b value, and it's representing decay. right? Multiplying by 1/8 over and over and over again makes the number smaller and smaller. To graph the function, we're going to pick a few x and y values. I've heard teachers say the big five, -2, -1, 0, 1, and 2, and those are pretty good choices. Excuse me. Those are pretty good choices here, but you may notice right away some values aren't going to be nice to use. Obviously, if I'm raising 8 to a power of 2, I'm going to get a 64, something that's racing off the coordinate plane. So we may want to not use all of those, but they're a good place to start. So let's see what happens. My y value here for -2, I'm just going to kind of pencil in a decay function should look something like that. So hopefully my points are showing that type of behavior. So if I plug in a -2, I get 1/8 to the -2nd power, which is the same as the reciprocal to the 2nd power, which is 64. Okay, that's off my graph. But at -2, I can put a point way, way up there just to let me know that it's starting up at a really high height. Next one, I've got 1/8 to the -1st power, which would be the reciprocal to the positive 1st power. That would just be 8. Okay, so that one is on the graph. Next one, I've got 1/8 to the 0th power, and anything to the 0th power is 1. Then I have 1/8 to the 1st power, which is just 1/8. And then I've got 1/8 to the 2nd power, which is 1 to the 2nd over 8 to the 2nd. That's 1/64, really close to that x-axis. All right, we know that that graph has an asymptote of the x-axis. It has not been shifted down to move the asymptote at all. So as we go through those points, we should see that graph level off, but not cross the x-axis. Okay, let's try number 18. I don't like the 1.8. I'm going to call that, what? That's 1 4/5, so that'd be 9/5. And we could use a calculator. We probably will actually here to construct our table of values. But if we weren't given a calculator, we could use that to help us out. Since this b value in here is greater than 1, we know that it is growth that it's showing. All right, so let's make our XY table here. I know that my graph should increase in height rapidly as I move to the right. So I'm hoping my points reflect that type of pattern. Let's see what we can actually fit on our screen. First thing, I want 9/5 to the -2nd power. Well, that would be like the reciprocal to the positive 2nd, which would be like 25 over 81. Not quite 1/3. So at -2, I'm about there. At -1, it's like the reciprocal to the 1st power, which is 5/9. It's that one, it's like 0.5 repeating, really close to 1/2. At 0, I've got 5/9 to the 0 power, and again, anything to the 0 power is 1. At 1, I'm not dealing with, oh, I'm sorry. That should have been 9/5 to the 0 power back there. It still equals 1, but we don't want the reciprocal anymore. Next one, I've got 9/5 to the 1st power, which is that 1.8. So almost 2. Then at 2, I've got 9/5 to the 2nd power, which would be 81 over 25. This time it's a little over 3. So we can see this time the growth is a little less drastic as the decay was in our last one, but we are seeing that graph gain height rapidly. It still does have that horizontal asymptote at y = 0. It is the x-axis, and it is still modeling that type of growth. So that's how we do that, and I did this whole thing without a calculator. A calculator table would really help us graph these much more quickly. I just want to show you how it's done without. Okay, next, word problems with this. And we've talked about this before. Often on standardized tests, um, you'll see some weird, bizarre formula with a lot of decimals, very intimidating, but it's just important to interpret what's going in and what's coming out of those functions in order to answer the questions that they've given us. Usually we're just plugging in values or evaluating some function. So let's take a look at 22. The population P in thousands of Austin, Texas during a recent decade can be approximated by that function where T is the number of years since the beginning of the decade. Tell whether this represents growth or decay. So again, no real work here, but looking at the number that's being raised to the changing power, it's 1.03. That is a growth function because our B value is greater than 1. Barely, but it's greater than 1. Letter B says, identify the annual percent of increase or decrease in the population. Annual. So what they want to know is, if we are kind of relating this, and this is just my thoughts here, if we relate this to our amount equals if we're relating this to that compound interest formula that we saw earlier, they say annual, so I know that n is 1. Then I'm starting to see a equals p to the 1 plus r quantity raised to the t power, because it's 1 times t. Okay, so now I'm just trying to figure out r is how much bigger is 1, or how much bigger is r value compared to 1. Well, r 1.03 minus 1, I'm just kind of solving for r inside this quantity over here. It's 0.03. That is a 3% annual increase. So a little bit of work converting decimals into percentages. Just move that decimal point 2 places to the right, as we've done in science class, I'm sure. Estimate when the population was about 590,000. For part C here. Well, remember that our function is working in thousands, so I want 590 as an output. I want that to equal 494.29 times 1.03 to the t power. And that's what I'm trying to solve. And we're going to learn how to solve this exactly once we get into logarithms later on in this chapter. But for now, what we can do is, they want us to estimate, but I really think that what we can do is use that life hack method in our calculator, and we will set y1 as our function. And we will set y2 as 590, and then we will do calc intersect. And I'm going to run through and show you what that gives me really quickly here. Let's see, y1 is going to equal 494.29 times 1.03, close the quantity, raise it to the x power. Our calculator has to use x as a variable. 590 for y2. Let's graph those. And as I'm graphing right now, I can see my calculator is not fitting that on the screen whatsoever, because my screen only goes up to a height of 10. So I'm going to choose the zoom fit option, and we've talked about that. It's zoom 0. And that will fit both of those functions on the screen for me, just to see a look at what they're looking like. And here it's plotting it out. It's kind of slow. While that's working, I did notice something that should have been changed here. They say that our output should be some number p. Instead of y, that should be capital P of t, just so we know that our output is a p variable. All right, we finished graphing. I'm going to do my calc intersect. And it tells me 5.988. So if we're supposed to approximate, it's almost 6 years into that decade. But that's how the calculator can help us out with exponentials. All right, example 4, it says rewrite the function in the form of, and we just saw this in the last example, y equals a times, it's going to be 1 plus or minus r, plus or minus, of course, meaning growth or decay, to the t power. Then state the growth or decay rate. Now, this seems like a really complicated problem, like we're not given enough information, but we actually are. We just need to apply our rules of exponents. So for number 30, y equals a times, I'm going to call this 4 to the 1/3 to the t power, using that power to a power rule that we learned back in chapter 5. So that means that y equals a times, I'm going to find out what 4 to the 1/3 power is. And it's 1.587. That means y equals a times, this is a number bigger than 1 plus 0.587 to the t power. So that means our rate is 58.7%. Again, taking that 0.587 and turning it into a percentage. Okay, let's see what the next one looks like. I've got y equals a times, I'm going to call this 3 to the negative first to the 3t. That means y equals a times 3 to the negative third to the t power when I use that power to a power property. So let's just find out what 3 to the negative third is. It's 0.037. Well, 0.037, I get that by taking 1 minus 0.963. So a little bit of numeric work on our part. Oh, not 9.63, 0.963. So we know that our R value is going to be negative 96.3%. Or we could say 96.3% decay rate. And again, because it's going down. Okay, our final example, use our compound interest formula. Here's where we have to incorporate that, what do we want to call it, that compound interest formula, and I've put that in the line of text with you, or for you here. So find the amount A in the account with a principal P of $3,500 after 6 years. Okay, so number 42, here our amount is going to equal what we put in, that's how I remember the P value, times 1 plus R, that's this percentage as a decimal, 0.0229, over N. It's compounded monthly, so that means N is 12 times per year, and that's raised to the 12 times per year times 6 years. Okay, and we're just going to use a calculator to figure all that out. We want to be careful with parentheses and all that good stuff. 3,500, let's open up some parentheses. 1 plus another set of parentheses for that fraction, 0.0229 divided by 12. Close the fraction, close that whole quantity, to the, and then in parentheses again, 12 times 6 for that exponent. And I get 4,014.98. So $4,014.98 for that account. For the next one, number 44, same formula, but they're changing how frequently we're compounding the interest. A equals, we're still putting in $3,500. 1 plus, now our rate is 1.26%. That's 0.0126 as a decimal over daily. That's 365 raised to the N, 365 times T, 6 years power. Okay, and if you have a newer calculator, it's nice. You can hit the up arrow key and grab that formula that we just had. And I'm just going to change the numbers that we need to. I'm going to change that 12 into a 365 in both places. And for that one, I get 4,015. Oh, hold on. I didn't change that percentage. So I need to change that percentage from a 0.0229 to a 0.0126. Then hit enter. I get 3,774. That sounds a little bit better. And 85 cents. And again, we're talking about money, so our answer should be labeled in that way. All right, definitely got some new formulas, some new types of functions that we're seeing work here, but this exponential and logarithmic work has a lot of applications to the business world and to the science world, as we'll see all throughout this chapter. So it's very applicable. We see these functions a lot when we talk about things growing over time. They typically follow exponential growth. All right, so let's take a look at our assignment for this section. There you have it.